You've got 3 of us here today. There's a few more people at Ordnance Survey. There's over 1,000 of us. We're going to tell you a little bit of a story about how we've been trying to use deep learning for some of our work. But firstly, just to show you some faces, some easy slides to take you in. There's 3 of us. I take the glory. These guys do the work. We haven't got Jacob with us today, which is a shame. We've also been working with universities, so it's important to credit these guys who's helped us along the way with a lot of the ideas, developing what we're trying to do. University of Southampton, Lancaster University, and University of Liverpool. And they have introduced us to these 3 PhD students who are working on parallel topics, which we're not going to be talking about today. So, a little bit about who Ordnance Survey are. We are Britain's mapping agency. I don't remember these slides, oh God. We've been around for over 2 centuries, and we map in very, very high detail all sorts of things in the landscape, like buildings and roads. We map the height of the land in contours and in other data. And we're very much, data is about Britain, although we've started to face out and work with other mapping agencies and organisations internationally. A lot of what we do is actually digital data. So people know us for our paper maps, but that's a very, very small percentage of what we're doing. And I'll show you some examples in a minute to give you a feel for what we're talking about. People often say, why on earth are people still researching at Ordnance Survey? Why is Ordnance Survey still in existence? Surely the landscape has been mapped. It changes an awful lot. So a lot of what we're doing is updating the data. We make hundreds, thousands of updates every week. And we do a lot of that using remote sensing, which is capturing data, in our case, from aeroplanes. And we think that because we fly between March to November and catch masses of data, particularly in years like this year when there's been a lot of sunshine, we're probably one of Britain's largest capabilities for remote sensing. So some examples of the kind of data we're talking about. So we're really talking about describing the landscape. This is a height model, so it shows the tops of trees, it shows the land height, where there aren't any trees or buildings on it. And we produce this almost as a byproduct of our flying. So this is not captured using laser scanning. Some of you might recognize LiDAR data. It's very similar, but we use our aerial imagery to create this. And if you want the details on that, we can talk to you about it afterwards. This is the kind of data that we work with, although this has been ortho-rectified, which is about taking the imagery from the aircraft and correcting it for the shape of the landscape and the shape of the buildings and the trees and everything. So the effect is that you're looking directly down. And that's a product that we sell or provide. Probably our most important product are these digital data, and these are vectors defining the detail of the landscape. So you can see the outlines of buildings there, you can see roads, even down to pavements, all sorts of other features that we capture partly using the remote sensing approach, but also with surveyors out in the field measuring these features. Take a little mental photograph of this, because we'll be talking about topographic data later. We've been using this quite a lot in our deep learning work, as well as the remote sensing data. And also, we automatically provide single heights for our buildings. We're very aware of what our customers need. They are provided with a great deal of data that we've just shown you, but their needs are changing all the time. And we know that there are hundreds, probably more than that, of individual features that they'd like to have that we can't currently give them. And that means that they're asking for bespoke products, and they're asking for us to turn around our product capture quickly. So that's a motivation for some of the work we're doing. Also, with our remote sensing capability, we're capturing lots and lots of data that we're not really pulling out a lot of detail from, and we'd like to use that far more. So this is the interactive part, so I'm hoping you're feeling awake. Just to give you another example of the kind of data we're dealing with in our research, as well as generally Ordnance Survey, can anyone shout out anything that they can see in this lovely image here? Any kind of description of it that they want to give us? Cars, thank you.
A railway.
Thank you, Charis. A railway, yes, there's a railway going through, which runs parallel to... Yeah, there's a road.
Dual carriageway.
Yes, the dual carriageway. Do the cars mean anything to anyone? What's anything special about those cars? Oh, very good. Almost certainly, yes. Southampton Port. So you've just looked at that. I don't know how many people work with remote sensing data. You're probably starting to make a few interpretations of the data that go beyond the kinds of building outline, road outline, the kind of details that we're capturing. So we know that there's masses of information in our imagery that we're not currently using. This is probably the big inspiration for what we've been doing. I will read out this quote and then interpret it in our language. Joshua Bengio in 2014 published this paper on representation learning, and he said, an artificial intelligence must fundamentally understand the world around us, and we argue that this can only be achieved if it can learn to identify and disentangle the underlying explanatory factors hidden in the observed milieu of low-level sensory data. Now, to interpret that in our world, we're seeing that as we could create something that interprets aerial imagery and finds in it buildings because we want it to go and find buildings, or finds cars because we want to find car parks. But it isn't truly intelligent unless it's actually extracted the underlying processes that have got that there as it is. So what we're trying to do in our work is pull out those factors that have shaped the landscape. So it's not just the human activity, there's the environmental processes that have gone along as well. And also we understand that the landscape that we're talking about is not just interlocking factors, it's also a hierarchical thing. So a building is part of a piece of land that makes up a property, which makes up a residential area, which makes up the suburb, which is part of a city. So there's a hierarchical factor. And we want to be able to actually start to pull that out as well in the work that we're trying to do. So having all these kind of, at the moment we've got a number of kind of loose concepts. Back in 2014, 2015, we decided we needed to research it a bit more, understand what we're trying to do and formulate it into some better ideas. So we started a one-year postdoc at the University of Southampton in conjunction with Lancaster University. And really it was about trying to understand what on earth was going on in the world of machine learning, because there'd clearly been some changes since the late 90s when I was doing it at university. And also understand practically how do you handle the data and what are the tools that you need to use. And just to show you some of the examples of the work we did in that first year, this is quite a nice example. It's from a 2012 paper by Charis and Ung. And it's something you can do at home. If you play with imagery at all, this is great fun. This is a CFAR 10 data set, which is tiny images. I think they're 32 by 28 by 28 pixels, so they're tiny, but you can see they're showing cats, birds, no toasters or washing machines that I can see, but they're very small images, which means you can have a massive data set on your own machine. And if you use something called k-means clustering, which is a very simple unsupervised learning technique that finds just individual clusters within your data, you can pull out some fundamental image characteristics. You have to achieve this, you actually have to do something called whitening as well, but again, ask later if you want to know more. So if we use k-means clustering and cluster to 100,000, these are the cluster centroids. And if you know anything about how the eye works, these look very much like the receptors in the early part of the visual cortex, which find things like edges, colours, point features. So that for us was quite exciting, but that was a CFAR 10 data set. What happens if we use our own aerial imagery? Now, this is not 28 by 28 pixels, so we had to learn to cut up the image into tiny pieces, which is exactly what we did. And then we applied the same process, and we got very, very similar results. So that's the CFAR-10, that's the aerial imagery, and you can see that the only difference really is in the colours. Doesn't tell us a great deal about the landscape yet, but it does tell us that the image domains are not completely different, although we argue there are some differences. Also, if you've had any experience with deep learning, I'll show you this result, which we still argue, although it was back in 2016, it's still one of our best results. And this was where we started to train deeper networks, in this case, AlexNet, which is an 8-layer network. We trained it with the input of aerial imagery against our output, which is the topographic data that I showed you earlier. And this is the result of one of our trainings, where we actually were able to predict a very, very rough version of our topographic data. Not something that we'd sell as a map, but it's interesting because the network appears to have overcome the problem of shadow on that road that runs through the middle, which is a huge problem with learning that we find with our data. So that was the end of a year. What that did was really teach us a number of things about how we train networks, how we cut up our data, some kind of basic but extremely useful activity that we did during that year. And we also came up with this diagram, this concept of what we're trying to achieve now. And that is that the landscape is encoding. It's an encoding of the environment. It's encoding human factors. And they have everything in it that we hope that we can pull out. We sense it with our remote sensing data. And what we're trying to do is decode those factors. And we're going to use those decoded factors to do two things. We've got two goals. One is inference and one is discovery. And we'll be talking about those quite a lot in the rest of the talk. So I'll go into a bit more detail about what inference is and then what is discovery. The inference is, you could say this is your supervised learning. This is the things that we know we want to find, but we don't know where they are. So for instance, this image here, we know that there are trees, we know there are hedges in, we don't know where they are. We want to use inference to find them. Ta-da, we found them. So inference is the easy concept to understand, and that's the one we can sell to the business because that's the one where they can understand, a customer has come to me and says they want zebra crossings. Can we use your inference method to find zebra crossings? The other approach, though, discovery, we think is probably more important. This is where we get ahead of the curve. This is where we're not directly answering a customer question, but where we might actually meet their needs in the future. And this is about those things that we pull out of the data. We didn't know they were there. We don't know where they are or what they are at the moment, but could they be useful to us in the future? So we're trying to find methods to actually see what our approach has discovered within the data. So after a year's postdoc, we were very lucky that John Hare here at University of Southampton was willing to carry on playing with our data. He's there in his not terribly large, extremely warm office. He's got several desktop machines under his desk, one of them with a GPU in it, and he trained some networks for us. He trained a much deeper network. So we had the AlexNet before. We're now working with a ResNet 50, which has got 50 layers. It's a much deeper thing. And he trained that by starting off initially with ImageNet weights. So ImageNet is extremely large data set. It's like the CFAR-10, but the images themselves are much bigger. And it's cats, dogs, birds, toasters, washing machines, all sorts of things labeled in the data, and there are millions and millions of examples and thousands of classes that it's labeled up into. And the nice thing about those is that people have already trained deep networks with them, so we can actually get almost off-the-shelf deep network that already has all the weights specified for the ImageNet data. And people are using that all the time now in various activities. So John took an ImageNet trained deep network and then did something called fine-tuning. So he retrained it with our aerial imagery. So he pushed the aerial imagery through and trained it against our topographic data. He also then took another deep network that wasn't trained with ImageNet. It started off with random weights and just trained it with our aerial imagery. So hopefully we have something that's going to do some great inference and discovery. Aha. Now, when it comes to inference, we need a problem. So we need to know what we're trying to answer. So to look at these networks that John had trained, we had some internal questions, things that we actually find quite difficult to find in our data. They are differentiating made from unmade roads, finding inland water, because inland water has every single colour you can imagine, and also discovering playgrounds. So we have some of these things already labelled in our data, but we don't have everything, and obviously the world changes and we're trying to find new examples. So we took some training data, we took our trained deep network, and we did a whole load of inference tests. And a little bit later on, I'll explain more detail exactly how we did those inference tests, but I wanted to show you our motivation for the next step of our research. So if we took just the pixel values out of the imagery and didn't use the deep network, so we just took pixels values out and tried to infer those made from unmade roads, the inland water, and the playgrounds, using a number of different options, we kind of got an average classification accuracy of around about 65%, thereabouts. So not great, not really what you want. If we use just the ImageNet weights, so the aerial imagery hadn't been passed through, that accuracy shot up. So it's just above, I should just learn these, shouldn't I? There we go. It's just around about 80%, which is kind of what you used to quote back in the 90s for your accuracy of any machine learning model ever. So it's okay, it'll do. So we fine-tune next with aerial imagery, so surely our results get better. They didn't. So with the fine-tuned network that had started off as ImageNet and then had the aerial imagery pushed down, our accuracies went down. Scratch-trained network, they dropped down even further. The worst part about this was both those networks took 3 weeks to train, and at best, it was as good as the ImageNet data. So why did we bother? The point is that we know that it should be better than the ImageNet trained network, because aerial imagery is different. It has differences in terms of how the patches are composed, because if we're cutting out these patches from the aerial images, we've not got a single object like a dog or a toaster in the middle of that patch. It can be anywhere. So the composition of the image is different. And there's all sorts of other aspects to the data that mean that we're sure that training with aerial imagery would be better. So the reason that our accuracies had dropped lower must be down to something in the way we've done the training. There are a number of different options in terms of the data. Maybe we didn't train with enough data. Maybe the labels were poor. We suspected that. Maybe it wasn't representative enough of the problem space we were working with, because it was only with Southampton data. And also, perhaps there were problems with the network. Could we use a different architecture or train for longer or a shorter amount of time? Could we tweak the hyperparameters? There's all sorts of questions around that. But that's a really, really high-dimensional space to be searching in. And searching in that when your training takes 3 weeks is really not practical. So, over to Olivia.
So yes, 3 weeks is way too long. Also, we ended up getting a load of out-of-memory errors all the time. So the one thing we decided to do was that we needed to decrease the training time, preferably to 2 hours, I think we wanted originally. But I still don't think we're going to get that. Yeah, we are. So going into this, we wanted to go into the cloud. And and as part of that, Microsoft were really interested in what we were doing and said, "Oh, we could help you." So we did this hack with them. Basically, we wanted to create an end-to-end process of putting all the data in the cloud, training in the cloud, creating a product, which would then remain in the cloud, just to kind of do a proof of concept of this entire end-to-end process. We crowdsourced a lot of data, so we had 20,000 labels of roofs, of either whether they were flat, hipped, or gabled, and we thought, right, that'll be enough to train with. We used one of their web services, which created an SVM after using ImageNet features. So you ran the data through through ImageNet and then trained the SVM against the classifications of flat, hipped, and gabled. And we managed to get 91% accuracy on 2 classes within the same geography. It didn't really work outside of that. But the key thing that came out of it was that we are now crowd ready. We can do everything in there that we wanted to, and hopefully that will give us a bit more of a speed up. So the next step was create a library to be able to do all our training. So we created Olivia, not my choice. But I'm Olivia, and we work in artificial intelligence. That's a Charis pun. It's built on Python, TensorFlow, and Keras. And one of the things that a lot of people ask is, why on earth are we using Keras? And basically, it had better error handling than Neon. Everybody seems to use it. Easier than programming in raw TensorFlow. It's got multiple backends, so that means it's probably going to be well supported. And when we started, PyTorch wasn't really as equipped as Keras was with the model zoo that it had. But we're still ambivalent and still open to new technologies, especially with the advances in things like fast AI that have come in the recent past. So we have a huge parameter space of everything that we could possibly change, and we needed to keep something constant. So we decided to stick with ResNet 50 to begin with. It's an industry standard, but obviously there are other architectures available. We decided to parallelize to try and speed that up using the ROSM AI code, which provides several different parameterizations. And also going to using GPUs as opposed to CPUs. Keep the size of the data set the same, but also keep the magnitude of the data set the same. So we're keeping it to the ImageNet dimensions of 224 by 224 RGB and 1.2 million patches going through the network. We also decided that we were going to be using the Azure cloud computing solutions, but we needed to keep an eye on the usability because we kept having GPUs drop out on us and randomly only having 1 for some reason, when I was meant to be having 4. There's meant to be another slide in there that basically said, using all of these, we ended up taking the training time down from 3 weeks to 3 days. So that's a lot better. Also, we managed to get rid of all the out-of-memory errors whilst using the GPUs, which was good.
Okay, so we can start to iterate quickly now, so we're ready, we can solve our problems. But the next big problem was data, and almost no one who I've attended has really spoken much about data, and I still think, because it's my job in this team, that it's 90% of the work. So we decided we wanted to make cleaner classes, we wanted to make them more balanced, and we also wanted to make them more representative. So we don't just want to train in Southampton and then try and run it elsewhere. You kind of get this intuitive sense that a flat roof in Birmingham looks like a flat roof in Manchester. Spoiler alert, it really doesn't. So this is sort of what our classes could look like. This is OS master map data. We have 250,000 square kilometers of this with the matching imagery, which is about 4 trillion pixels in imagery, which then has a label underneath it, which is this map. We've also got 2,500 topographic classes. That's too many to train on, so I reduced it down to just these here, just something basic, so there's kind of 6 at this stage. And what I did was I took a smattering of points. So we work in spatial data, which is a bit rare, I think, but you just throw some points at some imagery, make a little box around it, which is the 224 by 224 pixels, and then you decide what the label is going to be by looking up, almost using MasterMap as a lookup table for what that patch should be called. Okay, so here's some patches. Yay, sorted. Except, data struggles all the time. So it's really not as simple as it seems. If I take a random smattering of points and one falls in the center of this patch, that tiny little thing in between those houses, which you can barely see in the actual image, is actually made silt surface. So I've labeled this entire patch made silt surface, and that doesn't really make much sense to me, so I have no idea how I'm going to train a machine learning algorithm to pick up on that. We do actually have some genius experts who probably could have picked up on that path running in between them, but that's not an ideal way to train an algorithm. So the next thing we did was look at different ways of doing this. So shall I just take the center of the patch? Well, no, we've just seen that doesn't really work. And here's some other examples where it doesn't work. And oh my God, trees. Why? Literally the worst part of this is dealing with trees, because we map what's underlying them. That's what everyone else cares about. Okay, so maybe I'll have a look at big things. Oh, no, that doesn't work at all, because then you end up with no roads, because no roads are 56 by 56 meters. You end up with no small water features, no individual trees. So I'm skewing my data by just using big things. Okay, so maybe I'll take the percentage of the patch. Oh, no, that hasn't really worked either, because some of these maybe could make sense to us, but the highest percentage in that center patch is a private garden. But really what's in the slap bang in the middle of it is clearly a building. So I don't really want to label that patch as, it's a nightmare. So eventually I came across this paper, which is talking about effective receptive fields, which is for image classification. So if you take the black box to be your image, what this paper basically said was that the white pixels in the center are the things that make the most votes on what the class is going to be at the end. So really, you want whatever the class is going to be somewhere in those pixels for it to pick up on it. So I sort of faked that. I cut out a load of patches, found the center of them, put a fake box over the top of it, and then said, if you take up the majority of that box, you can now be a patch. So this all sounds, maybe fairly simple stuff, but the key thing I want to drill into everyone is look at your data. It's so easy to say, and no one ever does it. So we used FME Workbench to sort all this out. It's mainly used for spatial data. If you ever do anything spatially and you have to do a lot of data ergonomics to it, I recommend FME. So it just works out sizes and widths and centers, and then that's what it actually looked like. It's a behemoth of death, but it worked. And it can also work on the server. So we just pump in our topographic layer, pump in our imagery, and it will then cut out these patches for us, and it creates 1.2 million in 6 classes. It did that in about 6 days with 5 pretty small engines. So yeah, there we go. We've got data now. We're ready. We're ready to go again. Oh, you've got one.
I think I might tap. Thank you very much. These are the wrong slides, aren't they? Yeah. Never mind, we'll carry on because we're professionals. Brilliant. Thank you, Charis and Olivia. So they sorted the problem, really, got the training right down. And so we needed a name for what we've produced. We've trained a network. We're going to call it TopoNet. So we're going to talk about TopoNet for the rest of the presentation. This is currently ResNet, so it's still a 50-layer network, trained with there's 2 versions of data that Charis has produced. The results I'm going to show you is version 2 of the data. There's version 3 to come up. Numbering system seems to be slightly out there. I'm going to show you some results. Yeah, version 1 was the Southampton data, we'll say. So, now the technical part. This is where we talk about what we mean by inference and discovery. So how are we doing these things? We've got TopoNet. We've trained that using our aerial imagery and our topographic data. And it's produced this box. Could call it a black box. Maybe it is, maybe it isn't. Customer comes along with a new problem. Perhaps they want to find solar panels on roofs. One way of doing that might be to then retrain TopoNet to identify solar panels on roofs. One problem that is that's retraining a deep network, and we have a lot of pain around training deep networks. The other thing is, to train a deep network, you need a lot of data, and our customer doesn't have a lot of data, so we've got a different approach. What TopoNet does, well, what it has at the moment with the 50-layer network, it's got over 22,000 filters. So these are the nodes in the network, each of which responds to the input data and outputs a value. So we can use the trained TopoNet as a feature extractor and get out over 22,000 features for the input data. So that's how we use it. We push in our aerial imagery and we extract the 22,000 features. And then we use those with a shallow network, a support vector machine in our case, because they're quite good with small amounts of data, and the labels that the customer has given us to create a simpler network that predicts whether there are solar panels on the roofs or not. And this is what we're calling inference. Ultimately, our idea is that we would use this process at a production scale to produce a product or perhaps a service. Similarly, although we're not really sure how we're doing the last bit yet, so we want to do some discovery. So we can extract those features and look at them and see what they mean. Do they mean something individually? Is there an individual, each of the 22,000, do they have an individual meaning, or together do they have some kind of meaning? We're not really sure we're doing that yet. But if we can look into what the network has learned, can we actually find further products or services for our customers? So that's our discovery aspect. So we've got TopoNet. We're calling it TopoNet version 2. It's with version 2 of the data. We can now iterate quickly. So we can change all those parameters that we think are making our inference poor. The last aspect really is, if we're going to start iterating quickly, we really need to have some metrics that we're working against. So because we really like to push all ourselves into a room together and switch off our email. We had another hack like the one we had with Microsoft, but we just did it internally. I say that, but is this working? There we go. The furry guy up there, he's actually from Microsoft, but we've got a tame Microsoft guy who comes and works with us now. Yeah. Thank you. So we had a week together where we tried to create some metrics for inference so that when we create a new network, can we see how quickly it infers? And also looking at the discovery aspect. And I'm actually going to whiz through these slides, but if you've got questions on the discovery aspect, please ask them. So I'm just giving you some teasers at the moment of the discovery. Thank you. One aspect of whether we've discovered something or not is, what does it mean to a human being? So Charis has done some really good work in actually getting some crowdsourced meaning to our filters. So each one of these squares represents the filter in the deep network, and it represents what that filter most highly responds to. And we can ask people what colours that particular filter seem to respond to, what particular objects, what shapes. Other things that are in the data, and we can start to understand whether there are aspects of the network that are useful to us. For instance, whilst we already find buildings and roofs and things, we don't currently find zebra crossings, but it looks like there's a filter that someone's identified seems to be responding to it, so that could be useful. Further, if that filter is responding very cohesively, so all 16 little squares in that, are the same thing, then we know that it's a very strong responder to that thing, the colour, the object, or whatever. We found that as we go into the network a bit deeper, the later filters don't seem to be so clearly responding to things that people understand. We've got to do a lot more work around that. We don't really understand what's going on fully within the network yet. So we're starting to understand TopoNet. We're understanding the kind of things that TopoNet responds to, what it likes. Can it infer? This is the thing that we're really interested in terms of selling it back to the organisation so that we're allowed to carry on doing our work. It's a new world. We've got new problems. Customers are asking us for roof shapes, and they're asking us for roof materials, amongst other things. So we tested our new TopoNet against some of these particular problems. Now, just to show you, if we take our features out of ImageNet, so we're still comparing against the ImageNet weights, we can get, for the roof type, for the particular classification problem we had, 50% accuracy. That's poor. With our TopoNet, we got up to 80% accuracy. Yes, we are better than TopoNet now. ImageNet, sorry, thank you. Whew. It's a bit late, isn't it? These are the ones I'm whizzing through because they weren't meant to be there. For roof material, using ImageNet, we were getting a 65% accuracy at best. TopoNet, we're up to 90% accuracy. We're winning. Finally, we're training networks that are doing something useful for us. Right. So, there we go. Just to show you, TopoNet consistently above ImageNet. So the next step really is to try and scale this up. Can we actually make this work in a production sense? So that really involves understanding better how things are going to work within the organisation, and maybe iterating to create a better TopoNet. The result would be, if this image on the left is kind of demonstrating what we would have. For the building polygons within our data, we'd actually apply the roof material to the building polygon as an attribute, or the roof shape, or something like that. So, just to summarise, we're using deep learning for both inference and discovery. And the inference aspect is much easier to understand, but we think discovery is ultimately going to be more important. Really, really important aspect, it's hard to overemphasize, is that it's important to have very, very clean data. We've moved from on-prem machines into the clouds, but we might be moving back again for various reasons. And we're now in a position to keep iterating over TopoNet and to scale up where the organisation wants our results. Oh, that's nice. That's just showing all the various other bits of work that we've done as part of this project. It all kind of fits together quite nicely. So just to conclude, we still think that data cleaning is 90% of the work. It really is important. It was not simple or painless to speed up training, and cloud resources are difficult. We still need to be better at understanding the discovery aspect of what we're doing, but the inference is finally starting to work, and we're looking at taking that beyond research into the organisation. Thank you very much.